Now that we know how to describe the speed of a reaction using rate laws and how to determine rate laws from experimental data, we're going to use those ideas to describe another phenomenon, and that is equilibrium. We've previously talked about equilibrium when we looked at the water evaporation bottle, where we had, it was about 2 months ago, still sitting here on the front counter, where we had liquid water evaporating to a gas and gaseous water condensing back into a liquid. But in our closed bottle with the rubber stopper on the top, the evaporation, the water can't escape. And so what develops is a system where overall it doesn't appear that there's any more water evaporating because it's reached a state where the amount of evaporation is equal to the amount of condensation, and that is what we call the equilibrium. We're going to talk about equilibrium now instead of a physical process in terms of a chemical process, where we have two opposing forces, two opposing processes, and they're happening at the same rate. So in equilibrium, in more general terms from what we've talked about before, in equilibrium, we have here for a reversible, and it has to be reversible chemical reaction, for reversible chemical reaction, we have the rate of the forward reaction is equal to the rate of the reverse reaction. That says reverse. Reverse. My board never works for me. So the rate of the forward reaction is equal to the rate of the reverse reaction, which means that overall we don't see a change. Please note, as it says here, that equilibrium does not mean there's an equal amount of product and reactant. Think about our bottle of water. I mean, we have much more liquid water in our bottle than we do gas. It's at equilibrium. It simply means that the rates are equal to each other. So our example that we're going to look at here, we have 1 mole of hydrogen plus 1 mole of iodine going to 2 moles of hydrogen iodide. And we know we can write a rate law for this. So our rate of our forward, so let's see here. So this is going to be, and we know from our double-headed arrow here, our two harpoons, forward is, of course, going from left to right. So forward is going that way, and reverse is going back. So our rate law, if we wanted to write our rate law, assuming this is an elementary step, a rate determining step, the rate law going forward is equal to a forward rate constant times concentration of H2 times concentration of I2. If we want to talk about our reverse reaction, our rate is going to be a different rate constant, so rate reverse times concentration of hydrogen iodide, and since there are 2 HIs, we would have HI squared. Well, at equilibrium, we know rate forward is equal to rate reverse. So let's set these two equal to each other. So here we have, in our forward reaction, we have K forward times H2, concentration of, times the concentration of I2, and remember you need to use square brackets, times, or is equal to, excuse me, the reverse rate constant, so Kr, times the concentration of Hi squared. Well, we're going to rearrange this equation so that we get our equilibrium constants on one side and our concentrations on the other. So we're going to rearrange, and we're going to get K forward over K reverse is equal to concentration of Hi squared over concentration of H2 times the concentration of I2. This right here that I've written in red is KEQ. K is the constant EQ equilibrium. So as I mentioned when we introduced the rate constant, for the rate constant I use a lowercase cursive k because we have more k's coming, so here's our next k. It's a capital K and a subscript lowercase eq, KEQ, and it says here that is what we call the equilibrium constant. It is for this reaction, for this equilibria, at at its specific conditions, temperature, pressure, the whole deal, we can describe the concentration of all of our reactants and products by this expression once they've reached equilibrium. So KEQ is HI squared, for this one, HI squared over H2 times I2. So here's another example on the bottom. What would be the KEQ for 2H2 plus O2 goes to 2H2O? Well, I really don't want to have to do this entire derivation every single time we go through and try to find rate or an equilibrium. However, you may notice, and if you haven't already, take a look, the expression that we just wrote for our KEQ is directly related to our expression above. We have our products, HI, and there's two of them. So if we have here, if we look up at the top, we got HI, 2HI, and that's what we have down here in our numerator, HI to the second power. And then our denominator of our KEQ expression comes from our reactants, H2 and I2, 1 mole of each. So down here we have H2 to the first power and I2 to the first power. So what would be the KEQ expression for this new equation? We don't have to do the derivation. All we have to do is say KEQ is equal to, and I look at my product, so I have H2O, so I say concentration of H2O. There are 2 moles in the balanced chemical equation, so this is H2O squared, over, and I have H2 on the bottom. There are 2 moles of H2, so it's H2 squared, and concentration of O2, 1 mole of it, so it's O2 squared. So there's our KQ that we can write directly from our balanced chemical equation. So we don't have to derive it every time. We just look at the equation. We know that there is going to be an equilibrium expression because right here in the middle we have the equilibria arrows. And so we just say it's the concentration of every product over the concentration of every reactant, all raised to their stoichiometric power. It is always, I'm going to say it again, it is always, write it down, up here next to equilibrium constant, this is always products over reactants. Always products over reactants. That is the most common thing. Actually, it's really the only thing that's commonly goofed up. Products over reactants. Just like if we're trying to find something, find a slope of something or change of something, it's always final minus initial. It's always the end minus the beginning. So this is no different. Products minus reactants. Got it? Products minus reactants. Don't screw it up. So flip it over to the next page, and we have a reminder, one more time, equilibrium constant, numerator, concentration of products, denominator, concentration of reactants, and all those exponents of the coefficients from the balanced chemical equation. So here we have another example, right? The equilibrium constant KEQ for, well, I'm just going to start off by writing, I'll switch back to blue, start off by writing my big line down the middle. So here's writing my fraction. Concentration of what goes on top? Hopefully products went through your mind. And O2, that's a product, raised to the 5th power, times the concentration of NH3, raised to the 4th power, divided by our reactants, NO to the 4th power, and H2O to the 6th power. So KQ equals products to their coefficients over reactants to their coefficients. If we think about what this means, we said there at the beginning on the previous page, equilibrium does not mean there's an equal amount of products and reactants. So what is the number, what does the numerical value of KQ actually tell us? That's its significance. If KQ is a really, really big number, that means that my numerator is going to be a lot bigger than the denominator, which means that I'm going to have many, many more products that are formed. If KQ is very, very small, And now KQ can never be negative because that would mean you have a negative concentration, and you can't have a negative concentration. But if KQ is very, very, very small, so 10 to the negative 30th, let's say, that means that there is way more reactant than product, and so there is there's very, very little product that's formed. We got a couple example problems down here. KQ, what is the value of the equilibrium constant for this if, and we have concentrations. So we need to first write our KEQ expression. KEQ, so KEQ is equal to products over reactants, so concentration of NOBr squared over concentration of Br2 concentration of NO squared. And in this case, I have values, so I just plug in my values. Concentration of NOBr, it says, is 0.0667 squared, that would have been bad, divided by 0.214 for the concentration of Br2, and the concentration of NO, 0.428 squared. So then we just plug that into the calculator, and so we got 0.0667 squared divided by, and be careful when you're plugging these into your calculator. Please, please, please double check your math. Make sure that your denominator totally stays in the denominator. Best way to do that, when you put it in your calculator, put extra parentheses right here. Open parentheses, put everything in, close them, and then hit equals. And in this case, we should get a final value of 0.113. So 0.113, that's the KEQ value for this expression, or for this reactant at 68 degrees Celsius. When we give you these problems, there's always going to be a temperature there. You don't use it. It is extra information that doesn't go into the problem. It's just mentioned because if the temperature changes, so does equilibrium constant. Number 2 asks us a different question. Number 2 asks, what is the equilibrium concentration if we have our KEQ value? So for this one, let's make it go. We'll get that one just barely on screen still for you. There we go. So we have our equilibrium expression, or value, I should say. We have the chemical equation there on the right. So we first need to write KEQ is equal to concentration of NO2 squared over the concentration of N2O4. In this case, I have KEQ, so I'm going to write that in. KEQ is, let's see. Yep, there we are. All right, so KEQ is equal to 4.61 times 10 to the negative 3 is equal to the concentration of NO2 is what we're looking for, so NO2 squared over the concentration of N2O4, which is given to us in the problem statement, which is 0.277 molar. So then we solve for that concentration, and just like we did before, you can solve for it algebraically first and then plug in your values, or you can just plug in your values. So in this case, we get the concentration, let me come over here, the concentration of NO2 is equal to the square root of 4.61 times 10 to the negative third times 0.277. So I multiplied both sides by 0.277, then took the square root. And this equals 0.0357 molar. There's my final answer. So KEQ expression allows us to describe what is the relationship between reactants and products, where does that equilibrium lie, And then we can solve for either the KEQ if we know the concentrations, or if we know KEQ, solve for a missing concentration.